Hello everyone, welcome to week 12. So this week we will continue to talk about cache. We will introduce different types of cache, how to improve the cache efficiency, the design of the cache, how to be more efficient, how to design a more efficient cache. And then we will also, after I record this video, I will post a quiz for cache. So I was originally planned to have a lab for this week 12 as well. But as some of you are still working on the midterm exam, so I determined to postpone the lab to week 13. So I will update the schedule, the weekly schedule a little bit. So you will have a lab for week 13, focus on cache simulation, cache simulation. So for week 12, I will post a quiz, a simple quiz. So in the next video, I will talk about the exercise problem. So I will do a couple example problems, which is really similar with the quiz problem. So please watch this video and next video, and then you will understand the basic concepts of cache design, different types of cache design, and watch the video for the exercise problem, and then you will be ready to finish the quiz problem. Okay, so in last video, we have introduced a direct map cache. So we have introduced the general structure architecture for the memory design for high performance computer. So a cache is really important for a high performance computer because most of the time, so in general, most of the time, the most confusing, the most comprehensive, expensive operations for a high performance computer is loading or storing, load or store data from the memory into the memory, from the memory to the memory. So the memory communication actually takes the most of the time. So how to make the memory access to be more efficient is kind of like one of the most important questions for high performance computer design, So in last video, we have talked about the direct map cache, and I would like to give you a quick review about the cache design and how to use the direct map cache. So I got a couple questions about the direct map cache in the past week. So I would like to give you a quick review how to use the direct map cache, and we will introduce some other types of cache today. So in your slides, there's also some many more pages about the high efficient cache design with bigger block size and some other discussions about a real example cache, real cache used in daily life. So I will skip those pages for now. So we will focus on the most important part for the cache design, or it will take me maybe a couple more weeks to finish all the different types of cache design, but we will introduce the most important part. So I will skip a few pages in the slide. So just want to mention that please pay attention to watch the video. So if you use the slide to read it by yourself, it's super hard to understand. So the direct map cache, a quick review will be, so no matter whatever cache, we'll introduce set associative cache and fully associative cache today. So direct map cache is a unique example, is a special example for set associative cache. So so for all the different types of cache, so how we are using them. So this is our CPU or the processor, right? And then we usually need to communicate with the main memory, which is the RAM, because all our data and program, they're stored in the RAM. So the communication between the CPU and the RAM takes a lot of time, and people thinking about how to make this more efficient for the modern computer design come up to the idea of cache. So we have like, you could view it as kind of like a middle things in the like a piece of temporary storage, between the memory and the CPU, Or you could even view this as kind of like one piece of circuit altogether, one piece of circuit altogether with the CPU, and this is called cache. This is called cache. So it is located at between the CPU and the memory, between the CPU and memory. And usually this is much smaller compared with the RAM, because it is much more complex and much more expensive to make the cache compared with the RAM, okay? Because it is expensive and it is much more complex. The circuit is much more complex compared with the pure memory inside of the RAM. So also it is fast. It is fast to get a piece of data from the cache compared with get a piece of data from the memory. So this is in general true. Everybody understands this, but in reality, so I don't know how deep you understand this. So like last video, we have introduced the direct map cache, and some of you asked me, well, for me to store a 32-bit data inside of the cache, so of course I still need to store the whole 32 bits because I don't actually know what is the data. So there's no way for me to store only part of the data, okay? So I want to emphasize, so each piece of data originally inside of your memory, if you have an apple here and you would like to store it as a copy of the apple, so what you have to spend is not only the apple, you do not only have to copy the apple into your cache, but you also need to store the address of the apple. So that means you are actually storing not only the apple, but also a piece of address for the apple. So you kind of like double whatever you want, because you will, if I need to store the apple 10 times, not the apple, if I need to store 10 different things, then I will need 20 different things. So one piece of data, one piece of address, because I don't actually know what is the content of the data. So I have to make a 100% copy of the data. So I have to do 100% copy of the data. And at the same time, I have to copy the address of the data. Because when your CPU try to read anything, or write anything, the only thing you know is the address. So the only thing CPU knows is the address. The only thing the CPU have is the address. Of the data. It does not know the content of the data, right? So there's no way for me just to do a copy of the apple. I have to copy the address of the apple. So this is like a, one complex part of why the cache is expensive. Because you generally spend a lot more space to hold a copy of the data you want. So in general, because this is small, so I cannot put everything into the cache. So if I have 100 elements here, I probably only able to hold 10 of them. So then how can I make a more efficient cache? Then I really wish I could select the 10 elements which are used all the time, and I keep using them load them from the cache, and I don't need to go back to the memory to get them, right? So how to select the different things from the memory is a big question, and nobody have that 100% most accurate or most efficient way to pick all the most important data. But however, you are able to select more important data in general. So you could in general find the data which is used more often, or you could actually find some data is used many times. So you would like to keep that piece of data in your cache because your CPU want to use it many more times, so you don't have to go to the memory to load it again. So this is in general how the cache work, right? And then we introduced the a couple examples last time. So one example I told you, for example, if I would like to design my cache with 4 different words. So 1, 2, 3, 4, 4 words, 4 words. So the cache capacity is 4 words because I could store 4 different things in it, and each one is a word. And in general, we call each part here as a block. So remember the general concept we have introduced the last time. So we call each unit, each box here as a block, And the most common size for the block is 1 word, The most common size for the block is 1 word. So you could have one term called block size, and that generally means how big is 1 unit, inside of your cache, and how many blocks you have. You could have 4 blocks, you could have 8 blocks, right? And how could we determine for me to store each piece of data? So each piece of data here is 1 word, If I would like to store 1 word inside of the cache, so I do not only need to store the pure 32 bits data, I also need to store the address. However, people figure out I do not need to store all the 32 bits address of that data. Instead, I can store part of it, part of the 32 bits data, and we call it a tag. And there's another term called the size of the tag. So that actually means how many bits address you need to store for each 32 bits data. How many bits address you need to store for each 32 bits data. So how many bits I need to store for a 32 bits data for this particular example? Suppose I have 4 words and 4 blocks inside of the cache. So I will have to indicate this is the first cache, second cache block, third cache block, fourth cache block. So I will have a cache index. And suppose I have 4 different locations, then I will need to spend 2 bits as my cache index. And then you figure out, okay, so the first cache index, the second cache index, they are actually the same thing for like the 2 bits inside of the address, the 32 bits address. So this is the whole 32 bits address as we are storing word by word. So the lower 2 bits, they are always 0. You never deal with an address which end with 01 or 10 or 11. So all the address we're dealing with, they always end with 00. So I don't have to memorize the lower 2 bits of the 32 bits address. So first of all, I don't ever need to worry about the lower 2 bits. So I only need to worry about the 30 bits here. And within those 30 bits, remember, so we follow the principle that the first address, the first block in your memory will map to the first block in your cache. The second block in your memory will map to the second block in your cache. The third block in your memory will map to the third block in your cache. And the 5th block in your memory will again map to the first block in your cache. So as we are following this principle, so we actually do not need to store the 2 bits after the lower 2 bits. So we do not need to store the 3rd and the 4th bit inside of the address because that's identical with the cache index. So by looking at which location it is inside of the cache, so it is actually guaranteed. So the 00 address, whoever end with 00 inside of the 30 bits, they will map to this location. Whoever end with 01, it will map to this location. So we actually know that 2 bits. So we do not need to store those 2 bits. And for us to remember what is the address of the current data, we only need to store the 30 minus 2, which is 28 bits, So that actually tells us the rule of determining the tag is we always use 32 minus 2 and minus the log 2 of the number of blocks. Log 2 of number of blocks. So if you have 8 blocks, then this number will be 3. This number will be 3. If you have 4 blocks, then this number will be 2. This number will be 2. So one more example. So suppose we have 8 blocks, and in future we will call each block as a set. So it's actually one row. Inside of your cache, right? So you have many rows. You could have 8. Generally, you can have 8 rows, 4 rows, 2 rows, so whatever, right? So as later on, we'll introduce some other type of cache, not only the direct map cache. So we will start to call each block as a set. Okay? So suppose we have 8 sets instead of 8 rows instead of 4 rows. So then I will need to use 3 bits. as the cache index. And inside of my 32 bits address, so you will have 32 minus 2 because you don't actually need to worry the lower 2 bits. It is called byte offset. They're always 0. And how many bits we need to store as a tag? Because we do not only need to store the data, we also need to store the address of the data. However, the tag here is a little bit shorter compared with the previous example because I will need to spend 3 bits for a set index, right? So remember, there are 8 of them, so you need to spend 3 bits for each of them as an index. So it will be 32 minus 2 minus 3, which is 27. So I only need to store 27 bits instead of 28 compared with the previous example because I have 8 different sets, 8 different rows. And each of them will cost me, to represent the index, for which row it is, I actually need to spend 3 bits. So the tag will need to be, so the leftover is the tag. So you have to keep the tag, which is 27 bits. So when you, how to use the cache? So we look at some example last time. So for example, if I have 1024, so I have so many sites, so many rows for my cache. And remember, each block here is a 32 bits data, right? However, I do not need to store all the 32 bits address for each 32 bit data. So the lower 2 bits, they're always 0. And remember that I have 1,024 different rows inside of the cache. So I will need to use 10 bits to indicate which row it belongs to, right? So I don't have to keep those 10 bits here inside of the cache. Inside of the cache memory, I do not need to keep that 10 bits. So that 10 bits is actually used, it actually remembered, it's already implemented. So I actually know that 10 bits, because that's identical with the cache index. So the cache index. So the tag size will be 20 bits because that's the leftover you have to remember. The tag size will be 20 bits. So how do I use this example? So when I have something stored in the cache and I would like to load it from the cache instead of load it from the memory, right? So we would like to figure out how we can get a piece of data from the cache. And remember, this is your whole cache storage. That's here. And whenever you have a piece of data, so suppose the CPU is performing load from a particular memory address. So your memory address can be 001, 001, 0000. For example, like the starting point of our data segment. Suppose we're loading from this particular memory address, and this might be a label. So see this might be a label inside of your assembly code, right? So how this could happen in hardware? So when we're performing load using the CPU, then we do have the 32-bit address as our input, right? So all we have, if we are the CPU, then all we have is the 32-bit address. So by looking at the 32-bit address, and I first remember the lower 2 bits, they have to be 0 because you're load word by word. And then I will take 10 bits. I will take another 10 bits, counting from the third. So why? Because that will be the index used. That will be the index used in the cache storage. Remember that you have to use 10 bits. You have to use 10 bits to indicate which row it belongs to, which row it maps to, right? So if I use 10 bits, that will tell me which row it maps to, which row or which set it maps to, right? So after I check the 10 bits, then it will lead me to the location of that row, the location of that set. And that set will not only include the 32 bits data, it also includes the leftover address. Which is 20 bits. However, remember, different address, they could map to the same set. Different address, they could map to the same set, right? So you're not sure if this is the apple you want. So you have to compare the 20 bits here with the real address, first 20 bits inside of the real address. So what we are doing is comparing the tag with the higher 20 bits, comparing the tag with the higher 20 bits of the address. And if they match each other, then you will generate a logic 1 here. If they match each other, you will generate a logic 1 here. Of course, you do have to guarantee if this set, this row is not empty. So you have to have the valid set is also true. If the valid set is also true, then you will have 1 and 1, which give you a 1. And the 1 here is used as a heat signal. The 1 here is used as a heat signal. So if you have a heat signal, that means you do we do find the data inside of the cache. So the 32 bits here, the real data can be moved out because that's what we want. That's what we want. That is the real data. So, and some of you ask me, how can you implement this equal sign here? So by hardware, if you would like to compare 20 bits by 20 bits, you could simply use bitwise AND, right? So the simple gates logic are able to finish this. We could use simple gate logic to finish this. Of course, there are a lot of different versions, some more advanced implementation, more efficient ways to do this. However, simple gate logic can implement. You could just implement simple gate logic. So suppose the valid bit is 0, then you don't have to check the tag. Suppose the tag does not match the higher 20 bits, then you do not check the valid bit, right? So we could do either way. So if you have a 0, then the heat will be 0, and you do not need to take the 32 bits data out. So remember, the block here is the real storage I have inside of the cache. And then all this piece of circuit, everything included in this figure, are implemented in the cache circuit. So for each cache, you do not only have the storage, so you do not need to you do not only store the data, you also need to store part of the address, and you also have some other combinational logic to implement the comparison of the address. So this is how we use the cache in general. Okay, so in reality, you have much more complex cache than this figure. However, in the exercise and the quiz, we'll have like a much smaller and simpler example than this. So we will look at more example end of this video and in next video. So then, so a quick review, still in general. So if we're looking at a cache design, so we should of course know the size of the tag, because this determines how many bits you have to store for each 32-bit data, right? So for each 32-bit data, then you have to store the data, and you have to store part of the address. And the tag is actually the part of the address that you have to store. And also we have to know the capacity of the cache. So what is the capacity of the cache? How big is your cache storage, right? So this cache is able to store 1, 2, 3, 4, 5, 6, 7, 8 different words, and each word is 32 bits long. So your cache capacity for this particular example is 8 words, right? Of course, you wish your cache the larger, the better. The larger, the better. And it is expensive, so you cannot always get a super huge cache, right? So because it is expensive. So the capacity of the cache means how many data, so what is the size of the data? It does not include the tag. It does not include the tag. It only means how big is the data the overall data size, how many words, how many bytes you could store inside of the cache memory. Also, another thing, the last thing will be the hit and the miss rate. So remember that we did one example in the last video. So for example, if you keep reading the different data, so you might read one piece of data many times. So the first time you read it, the first time you miss, you find that piece of data, then you will put it somewhere. Right? So suppose I put it in one location inside of my cache storage. So this is my cache storage, including the tag, the valid bit, and the data. So according to the address of each piece of data, then I could determine where it maps to. So suppose it maps to this location. So the first time I saw that piece of data, then I will have a miss anyway, because I don't have it in my cache, and I will put it in the cache. And the second piece of data, suppose that's a heart. So I will put the heart in another location. Suppose it maps to another location. And then suppose you keep reading this and this for many times. So this is a loop for like 100 times or 100 times. So even the first time you have a miss, and later on you will have hit. You will keep hit because they are loaded in a cache. Right? So then how can I calculate the cache hit and miss rate? It is pretty easy. It depends on how many times you loop, how many times you will repeat. Suppose this thing only repeat for once, and then you will have your miss rate 100%, because both of them are miss. So the first time you will have miss, and the second time you will have hit. And suppose you will loop for only twice, then your miss rate will be 50%, right? Suppose you loop for 5 times, and you will have hit. 1, 2, 3, 4, 5. Suppose I loop for 5 times. So this piece of program is implemented for 5 times, and I will have 2 miss, but 8 hits. So the miss rate will be 20%. The miss rate will be 20%. And suppose you loop this for 1 million times, so your miss rate is almost 0%. Your miss rate is almost 0%. So I guess everybody get the idea. So if you could successfully select the really important data, put them in the cache, of course, you will tend to have a really good hit rate. And this is what we have to simulate in the lab. So we'll have more example next week, and then you know how to implement that. All right, so that's the example we introduced last time. And as I told you, I will skip many pages about the real example. In reality, how the cache is designed with a bigger block size and some technical tips about how to design more efficient cache. So I'll skip those, but jump to, in general, different types of cache we have. So in general, we have not only the direct map cache, we also have fully associative cache and NV set associative cache. In general, both of them are called associative cache. So what is NV set associative? What is fully associative? So the general idea here is, a basic idea, first of all, is, so when you talk about NV set associative cache, it actually means you have a couple or a few different entries or a few different tiny blocks inside of one big row or one big set. Okay, so remember that we in the previous example, direct map cache, each location, each block, each set only has one unit in it. But if you break one set into a couple different pieces, then this is called NV set associative cache. And the fully associative cache will be, so everything is kind of like randomly placed in a whole bag, a big bag. So your cache, your entire cache does not have any fixed mapping principle. So it's hard to understand by looking at the concept, but let's look at the figure. So remember, suppose we have 8 different sites, 8 different blocks, 8 different words. So the overall cache capacity is 8 words. So you're only able to hold 8 words in total inside of your cache. For a direct map cache, so you will have 8. So we're looking at the cache this way. So you will have 8 different rows, and each row here is called one set, or one block. Okay, so you will have 8 different rows, and each row, each set, you only have one block. So one set equals one block. One set equals one block. And this is what we did in all the previous examples. Suppose you have 8 different words to store, and then you have 8 words for your cache capacity, and then the 9th location will map to the first location again, right? And the 9 plus 8, the 9 plus 2 times 8, the 9 plus, so the 0 and the how to say that? So any address modulus 8, if they equals to the same number. So like the 0 and the 8, the 0 and the 8 will map to the same location. The 1 and the 9 will map to the same location. So for the address, with the same result, modulus 8, they will all map to the same location. Right? So what is set associative cache? So the general structure is you still have 8 different words placed into your cache. So your cache overall capacity is exactly the same. However, inside of each set, so instead of having 8 sets, and then you only have 4 sets. And each set include 2 blocks. Each set includes 2 blocks. So you have 2 separate locations in one set, one single set. And when you do the mapping, then your first address will map to the first set. Your second address will map to the second set. However, of course, then you will do modulus of 4 instead of modulus of 8, because you only have you will only have 4 different index for your set index, because you only have 4 different set index. So then what is fully associative cache? So fully associative cache, instead of having 8 blocks, 8 sets or 4 sets, so let me call this 8 sides and call this 4 sides. And I only have one set, for the fully associative cache. So instead of having 8 sides or 4 sides, I only have 1 set. So I actually just will every location inside of my cache. They're like all the same. And whatever you want me to store, I will just put it in a random location. So this example, just like if you have a huge bag and you would like to go to a big storage to suppose you have a big you have a cart, you have a small cart, and you go to the library to find the books that are often read by your kids. So you're trying to borrow some books from the library. So inside of the library, which is your memory, there are a lot of books inside of the memory. And then you would like to pick some books and put them in your cart and check them out. So that's your cart is kind of your cache. Kind of like your cache. And inside of your cart, you might have a few different drawers. So the first direct map cache, you have 8 drawers. So if you see a book, like an animal book, you will put in the first drawer. If you see a science book, you will put in the second drawer. If you see a math book, you will put in the third drawer. So you always follow that kind of principle, but there are many math books, many science books, many animal books.